Hey folks, my name is Nathan Johnston. Welcome to Lecture 38 of Introductory Linear Algebra. In today's class, we're going to continue talking about eigenvalues and eigenvectors, but we're going to focus on something in particular that can go wrong with eigenvalues and eigenvectors. And then we're going to talk about how we can fix that up. Okay, so let's dive right into an example that will illustrate what can go wrong with eigenvalues and eigenvectors. Okay, so let's try to compute the eigenvalues and eigenvectors of this matrix here, 0, -1, 1, 0. Okay, well, we do the same thing that we always do. Start off by trying to find the eigenvalues of that matrix. And to do that, you set the determinants of a minus lambda I equal to 0 and try to solve for lambda. Okay, because it's 2 by 2, we can use one of our explicit formulas for the determinant. Subtract lambda off the diagonal, so you're going to get minus lambda. Leave the off diagonal entries alone, minus 1, 1. Okay, you compute that determinant, forward diagonal minus backward diagonal, so it's going to be minus lambda times minus lambda, which is just lambda squared. The minuses go away, double negative. And then another double negative here because you subtract the backward diagonal, so you subtract minus 1, in other words, you add 1. Okay, so to find the eigenvalues of this matrix, we set lambda squared plus 1 equal to 0. In other words, we try to solve lambda squared equals minus 1. And of course, that equation there does not have any real solutions, right? Because if you square a real number, you get a positive number. You don't get a negative number, right? You get something bigger than or equal to 0. So there are no real numbers that satisfy that equation there. So this matrix A does not have any real solutions, okay? There are no real numbers that are eigenvalues of this matrix. Okay, and let's think about this geometrically a little bit. This does make some sort of sense, because remember what eigenvalues and eigenvectors are. Well, eigenvectors are vectors that just get stretched by the matrix, and the eigenvalue is how much it gets stretched by. But this matrix here, it doesn't just stretch anything, because this matrix, well, if you look at what it does to the standard basis vectors, right, it takes E1 and it puts it up on the y-axis, and then it takes E2 and it puts it over on the left half of the x-axis, okay? And then once you use linearity and all that, you find that any vector v, what happens to it is it just gets rotated counterclockwise by 90 degrees. In other words, this matrix here, this is just a rotation matrix like we saw way back in week 4. In particular, this matrix rotates counterclockwise by 90 degrees by pi over 2. Okay, so if you ask the question, are there any vectors that just get stretched by A? No, every vector gets rotated counterclockwise by pi over 2. Every vector gets its direction changed. So no, like that's why there are no real eigenvalues or eigenvectors here. Okay, there's nothing that's just getting stretched. But there is still a solution. There's a way around this problem. There's still a way to talk about eigenvalues and eigenvectors, even for matrices like this one. And the answer is to go through something called complex numbers. Okay, so some of you might have seen complex numbers before in some other course. I'm going to talk about them as if you haven't seen them at all, though, just so that we're all on a common footing. Okay, so basically, the topic of today's class is complex numbers. Now, the idea here is that throughout your mathematical education, there have been a few things that you've been told that you cannot do. You've been told, for example, you cannot divide by 0. And you've been told that you cannot take the square root of a negative number, okay? And while these statements are true, sometimes there are ways around them, or sometimes they're only half-truths. For example, when you're told that you cannot take the square root of a negative number, really what we mean is that, there's no real number that squares to a negative number, okay? But that doesn't mean that you can't introduce a new type of number that squares to a negative number. And that's exactly what we're going to do, okay? We're going to introduce a new type of number, a new number that we're going to call I, okay? So this number, little I here, what it is it's a new number that we're sort of tacking on to the set of real numbers. It's not a real number itself, it's something that we're appending to the set of real numbers to give us a new class of numbers. And this number I, what it has is this special property that I squared equals minus 1. Okay, and this might seem a little bit silly or a little arbitrary or a little like, wait, but why can you do that? And the reason that we can do this is sort of remarkably, it doesn't actually break anything, okay? You can throw this extra number I in and do arithmetic with it, and basically everything just works out. None of the nice properties that you like about real numbers is going to break down if you use this number I. You can still do arithmetic even with this number I, just like you do with real numbers, okay? So for example, you can add these numbers involving I, you can multiply these numbers involving I, use distributivity, use commutativity, use associativity, and all these nice properties of real numbers, and they all carry over to this new type of number as well. Okay, so let's get some terminology out of the way. Okay, we're going to say that an imaginary number is a number of the form b times I, where b is a real number. So any sort of scalar multiple, any real scalar multiple of this new number I is called an imaginary number, okay? And I want to make it very, very clear that this name is not meant to be taken literally, okay? It's just, this name came about just as sort of in contrast to the name real numbers, okay? This isn't a real number, so it's an imaginary number. But don't take that literally, okay? Imaginary numbers, they exist just as much as real numbers exist, and just as much as matrices exist, and just as much as any other mathematical thing that we define exists, okay? So, I mean, we're not cheating or anything like that. We're just defining a new type of object, okay? Which we do all the time. It just maybe feels a little bit weird this time, okay? And then we say that a complex number, it's a real linear combination of real numbers and imaginary numbers. So any number of this form, real number plus imaginary number, that's what we call a complex number, okay? And we call this part over here, this A, we call that the real part of the complex number, and we call this piece here, B, we call that the imaginary part of that complex number, okay? And, well, you can add and multiply complex numbers just like you're used to adding and multiplying real numbers. Basically, nothing changes, okay? So let's just do a couple quick examples to try and get comfortable with it. Let's add up this complex number with this complex number. And my goal after the computation is to have it in the form real part plus imaginary part times I, okay? I want to know what the real piece and the imaginary piece of that number are. Okay, and the way that I'm going to do that is just basically regroup parentheses here, right? I mean, if these were real numbers or expressions involving real numbers, I would believe that, hey, I can just do sort of the 3 plus 2, okay? And then I can do 4i minus 7i, like I can regroup things like that. And you can, okay? Nothing surprising happens when you do arithmetic with complex numbers. So really, the real piece, or the real part, is going to be 3 plus 2, which is 5. And the imaginary part is going to be 4i minus 7i, you're going to get a minus 3i here, okay? The imaginary part is minus 3. Okay, so just regroup things. Combine sort of like terms, basically. You're combining all the I pieces and all of the not I pieces. All right, multiplication is similar, okay? Just do what you would do if these were expressions involving real numbers only, okay? If I had a product of two terms, two binomials, then I would FOIL them, right? Do first times first, last times last, and then the two cross terms. And I'm going to do the exact same thing here, even though they're complex numbers. I'm going to do 3 times 2, well, that's going to give me 6. And then I'm going to do 3 times minus 7i is minus 21i. And I'm going to do 4i times 2 is 8i. And I'm going to do 4i times minus 7i is minus 28i squared. Okay, nothing surprising there. This is just exactly what I would do if these were all real numbers. Okay, the only kind of weird thing that happens now is I say, oh, I squared, what is that? Well, remember, what is the point of I? I squared equals minus 1, right? So 28i squared, that's 28 times minus 1, so it cancels with this other minus sign out in front and becomes a plus 28. Okay, so that I squared is just another minus 1. Okay, and then again, you can just combine things. What is the real part after this entire computation? Well, it's 6 plus 28 is 34. Okay, and what's the imaginary part? Well, I've got a minus 21i plus 8i. That's going to be minus 13i, okay? Just add up the coefficients, minus 21 and 8. Okay, and then you're done, okay? That's the result of the multiplication. Okay, more generally, I mean, if you wanted a rule to write down for addition and multiplication, you just write down sort of the obvious thing that comes to your head for addition, right? Just add up the real parts. A plus C is your new real part, and B plus D is your new imaginary part. Multiplication is a little bit trickier, but it's just doing what we did up here. Okay, you expand out the brackets and regroup. You're going to get A times C in the real part, and then you're also going to get a B times D, but then a minus sign because you'll have an I squared, so a minus B times D in the real part as well. And the imaginary part just consists of the cross terms, A times D plus B times C. Okay, that's your imaginary part of the product. All right, so addition and multiplication are straightforward. Division is a little bit trickier. Okay, so let's go through an example to see how we could handle complex number divided by complex number. And we're going to have to sort of introduce a trick to help us with the computation here. Okay, so let's imagine that we wanted to compute 1 plus 2i divided by 3 plus 4i. Okay, and remember, I want my final answer in the form real number plus real number times I. Okay, so real part plus imaginary part. I want it in that form. Okay, so the tricky part here is I don't know how to divide by like something involving I here. I don't know what to do there. Okay, so what I'm going to do is I'm going to multiply and divide this entire fraction by something clever. Okay, I'm going to multiply the top and bottom by 3 minus 4i. And the reason that I'm going to do 3 minus 4i, the reason I'm multiplying and dividing by that, is I'm just taking what was on the denominator, this 3 plus 4i, and I'm switching the sign of the imaginary part. Okay, that's how I came up with 3 minus 4i there. I just switched the sign of the imaginary part. And now let's just go through the computation and see what happens here. Okay, certainly I haven't changed the value of the fraction because I'm just multiplying and dividing by the same thing, right? This just cancels out. But if I'm multiplying the top and bottom, well, if I do the multiplication on top, what happens is I get 1 plus 3, and then I'm going to get double negative here, 1 negative from the minus sign, 1 negative from the I squared, so I'm going to get 3 plus 8, so 11 is my real part. Okay, and then your imaginary part is just the cross terms. I get 6, but then minus 4, so I get 2i as my imaginary part on top. And on the bottom, something really magical happens. Okay, on the bottom, I get 9 plus 16 is 25, so that's my real part. And then what's the imaginary part? Well, minus 12i plus 12i. They cancel out. The imaginary cross terms cancel out. Okay, so what I'm left with after I simplify it this way is, well, what's my real part? It's just 11 divided by 25. And now what's my imaginary part? It's 2 divided by 25. Okay, so this is the final answer of this division over here on the left. Okay, and the trick to figure out what it is multiply and divide by this number here, this 3 minus 4i. This number where you flip the sign of the imaginary part, that's something called the complex conjugate of the complex number. Okay, so in other words, the complex conjugate of 3 plus 4i is 3 minus 4i. And you've probably seen a trick like this before with expressions involving square roots in the denominator. You multiply by something called the conjugate of that square root expression to sort of make the denominator simpler, to sort of clear it. Okay, and it's a similar sort of trick here. It's like the complex number version of that trick. All right, so yeah, so what is the complex conjugate? Well, the complex conjugate of a plus bi is a minus bi, and we denote it like this with this funny little bar over top. So if you ever see a bar like that over top of a complex number, that means take its complex conjugate, flip the sign of the imaginary part, but leave the real part alone. Okay, and for our purposes, the important aspect of the complex conjugate was that if you multiply a number by its own complex conjugate, then the imaginary part, the two cross terms, they just cancel out with each other. So the imaginary part equals 0, and you're left just with a real number. Okay, so it's kind of a difference of squares sort of thing. The two cross terms cancel out with each other, and you're left with a real number. All right, so with all this stuff under our belt, now we can start asking questions like, hey, what are the roots of this polynomial, even if that polynomial doesn't have real roots? Okay, and well, if we start off with quadratics, for example, with quadratics, you can just use the quadratic formula. Okay, even if you end up getting square roots of negative junk. Okay, so let's go through an example here. Let's try to find the potentially complex solutions of this equation here. So let's try to find all the roots of this quadratic, x squared minus 2x plus 2. Okay, use your quadratic formula. Okay, so remember it's negative b plus or minus root b squared minus 4ac all divided by 2a. Okay, where a, b, and c are the coefficients of this quadratic. So just plug in those coefficients of the quadratic. A is 1, so it's just a half out in front. B is negative 2, so double negative here makes it a positive 2. And then b squared minus 4ac ends up being 4 minus 8. Okay, simplify that a little bit. 1/2 times 2 is just 1. 1/2 times this whole square root. And what is under the square root? Well, 4 minus 8 is negative 4. So normally we would be like, oh shoot, I mean, this quadratic, it does not have any real roots. And that's true, it doesn't have any real roots. It does have two complex roots though. And the way that you can find them is just, I mean, imagine like do complex numbers, right? Like you know how to do arithmetic with complex numbers now. What is square root of negative 4? Well, square root of negative 1 is I. Square root of negative 4 is just going to be 2i. Okay, and the 2 will cancel with the 1/2 out in front. So all that we get here is just this 1 plus or minus I. Okay, so I'm claiming that those are two roots of this polynomial here, but really what does that mean? Like, so we really can't picture that on a graph or anything like that. So what does it mean for 1 plus I and 1 minus I to be roots of this polynomial? Well, one thing that it means is that if I plug these numbers into this polynomial, I'm going to get 0. Okay, so let's check that. Let's try plugging 1 plus I into this polynomial and see what we get. So I replace every instance of x with 1 plus I. Okay, so I get 1 plus I squared minus 2 times 1 plus I plus 2. Okay, and let's just expand that out and simplify. When I do 1 plus I squared, I'm going to get 1 plus double the cross term, 2i. So complex number multiplication is still commutative. Don't worry, cross terms do combine like this. And then plus I squared, which is minus 1. All right, and then minus 2, and then minus 2i, and then plus 2. All right, so that's what it looks like all expanded out. And now you just start looking at terms here. Hey, I've got a plus 2i, I've got a minus 2i. Oh, those cancel out. Good. I've got a plus 1 and a minus 1. Oh, those cancel out. Good. Minus 2 and a plus 2. Hey, everything cancels out. I just get 0 at the end of the day. So yeah, 1 plus I, it really is a root of this polynomial. Okay, we could also plug in minus I everywhere. Okay, 1 minus I everywhere, and that's also going to be a root. I skipped over that calculation, but you can check it on your own if you want. Another thing that it means is, well, think about if you had 2 roots of a quadratic. That would mean that you could factor that quadratic as linear term times linear term, where like it was x minus root times x minus other root. With complex roots, you can do the same thing, okay? With complex numbers, well, I'm going to do x minus one of the roots times x minus the other root, okay? So 1 plus I and 1 minus I. And if I multiply that out, I'm going to see that I get exactly this polynomial, x squared minus 2x plus 2. So let's do that multiplication. Okay, expand out these brackets. You do first times first, oh, that's x squared. And then the 2 cross terms are going to be x times minus 1 minus I, and then x times minus 1 plus I. So here's my cross term, right? It's minus sign in front of the both, and then I add up the coefficients, okay? And then last term is going to be last times last, okay? So that's what I've got over here. And if you simplify that all down, here I've got plus I, minus I cancels out, so I just get a cross term of minus 2 here. And you multiply those out, well, those are complex numbers, complex conjugates of each other, so you get a real answer, and that real answer you get is 2. Okay, so just do all of this simplification, and you find that, yeah, you get exactly the polynomial that I started with. Okay, and this is sort of the key aspect of complex numbers here. Okay, complex numbers, they work really well with polynomials, and oftentimes, even if a calculation has complex numbers as sort of an intermediate step, you can get like a real final answer out of it. Okay, so like if you were asked, hey, how can I write this as a product of 2 linear functions? Well, if you're restricted to real numbers, you can't do it. But if you're allowed complex numbers, you can do it. Okay, this real polynomial can be written as a product of 2 complex linear polynomials. So even though there's complex junk at the intermediate steps, the final answer is still real. And that's kind of neat. And that's how they can be useful even for real valued problems. Now, one thing to notice about this example is that we didn't just get any 2 complex numbers as roots of this polynomial, but actually the complex numbers that we got are complex conjugates of each other, right? We didn't just get 1 plus I and then some other number. We got 1 plus I and its complex conjugate, right? The imaginary part had its sign flipped. Okay, and it turns out that happens in general, even for polynomials of higher degree, as long as the polynomial has real coefficients. Okay, so if you're ever working with a polynomial with real coefficients, its roots are gonna come in complex conjugate pairs. Okay, so if they have an imaginary part that's non-zero, well, there's gonna be another corresponding root that has the negative of that imaginary part. Okay, and we can go through a sort of a quick sketch proof of why this is true. So suppose you had some polynomial, so I'm just writing out the general form of a polynomial here, some real number an times x to the power n times, and then plus some number an minus 1 to the xn minus 1, and so on down the line with lower and lower powers, all the way down to a constant term. Okay, so that's just what a polynomial looks like. And well, suppose that you had some complex number that was a root of that polynomial. So some complex number that I'm just calling x star here. Okay, that's the root of that polynomial, which means if I plug it into the polynomial, I get 0. Okay, and my goal now is to show that its complex conjugate is also a root of that same polynomial. So I want to show that x star with a bar over top of it is also a root of that polynomial. So how do I do that? I'll just plug x star bar in, and what do I get? Well, I get, just by definition, I get this expression here. But then one nice fact about complex conjugates is that it plays well with powers and multiplication and all this stuff and addition. So I can pull all of these bars out on top of the entire expression. Okay, and this relies on those coefficients of the polynomial being real. Okay, what I'm doing here is I'm sort of using the fact that the complex conjugate of an is just an itself because it's real. And similarly for all of these other coefficients, they're their own complex conjugates. Okay, so I can just instead draw a bar over the entire expression here. And what that is then that's the complex conjugate of f just with x star plugged into f itself and the complex conjugate applied after the fact. Okay, but what is f of x star? That's just 0 because x star is a root, so this is the complex conjugate of 0. And the complex conjugate of 0 is just 0 itself. All right, and then that's the whole thing. Okay, now we've shown that yes, f at this complex conjugate equals 0, so that complex conjugate is a root. All right, let's give a little bit of geometric intuition for complex numbers, okay? The way to think about complex numbers geometrically is a plane. They're sort of two-dimensional numbers in a sense, right? Just like we think of the set of real numbers as a line, well, complex numbers we can think of as a plane. They're sort of like a real axis and an imaginary axis. So we can think about complex numbers very similar to how we think about R2, okay, two-dimensional real Euclidean space. The only difference is that complex numbers have a multiplication defined on them, whereas R2 doesn't. Okay, but otherwise we can think of them in the same way. We think of the complex number a plus bi as being the point with coordinates ab on that plane. So for example, the complex number 3 plus 2i, we would draw it at this point over here because, well, it's sort of 3 units over to the right, 3 units in the real direction, and then 2 units up, 2 units in the imaginary direction. Okay, and just to be really, really clear here, real numbers are complex numbers, okay? Real numbers are a special case of complex numbers where the imaginary component, the imaginary part, equals 0, okay? So in other words, real numbers are down on the real axis. So the number 5 here, it's just there on the real axis. It's 5 plus 0i. Okay, and I mean, there are lots of other numbers. I mean, it can be in any quadrant. Minus 5 plus I, that means you go left 5 units and up 1 unit. Okay, minus 4, minus 3i, now you're going left 4 units and down 3 units, and so on. And the complex conjugate also has a nice interpretation in terms of the complex plane here. The complex conjugate, all it is it's what you get if you reflect a complex number through the real axis. So if I want to know where the complex conjugate of 3 plus 2i is on the complex plane, what I do is I leave the real component alone, so I'm just going straight up or down, okay, and I reflect through the real axis. So here I go down 2 units to get to the real axis. So I go down 2 more units to get to the complex conjugate. So then I'm down at 3 minus 2i instead of 3 plus 2i. So complex conjugation is just the same as reflection through the real axis. All right, that's enough of that. Now we understand enough about complex numbers to be able to do matrix computations with them. So let's return to this original problem that we had where we want to find the eigenvalues and eigenvalues of this matrix, and let's actually find them now. They're not going to be real, they're going to be complex, but now we know enough to find them, okay? So let's find the eigenvalues of this matrix, and remember, we got this far before, okay? We found that if lambda was an eigenvalue, it had to satisfy lambda squared equals minus 1. Now we know what that means, right? Okay, we take square roots of both sides, and what we're going to get is lambda equals plus or minus square root of minus 1. In other words, lambda equals plus or minus I. Okay, be careful that you get the minus I as well. Okay, there are 2 square roots in that equation. Don't forget your plus or minus. All right, to find the corresponding eigenvectors, what you do is you pick one eigenvalue at a time and solve a minus lambda I times v equals 0. Okay, the only difference here from the previous examples that we saw in the previous lecture video is this time our eigenvalue is complex. Okay, so we're plugging in I for lambda here. Okay, so a minus little I times big I times v equals 0. That's the linear system that we want to solve. We throw it into an augmented matrix like usual. So we're just subtracting I off the diagonal. That's why I get those minus i's there. All right, I've got to row reduce this to put it in row echelon form. How do I do that? Okay, maybe this isn't super comfortable, but we know how to add, we know how to multiply, and we know how to divide complex numbers. Okay, so I want to add some multiple of the top row to get rid of this leading entry that's down here. Okay, and one thing that I could do is, well, I can take row 2 minus I times row 1, right? Because what's going to happen then is I'm going to get 1 minus I times minus I. Well, let's see, minus I times minus I is going to be minus 1. That's the elusive triple negative, right? It's going to be 1 minus 1 is 0 in the bottom left entry. That's why I'm doing that row operation. If you're having trouble seeing where this coefficient is coming from, just do division, right? You have to just divide coefficients to find what coefficient you got to multiply the row by to get rid of the other row. Okay, and then if we do the same thing in the second entry, this is going to be minus I times minus 1. Okay, so there's way too many negatives going on here, but what this is going to be is minus I plus I, which is also 0. Okay, so this minus I is also going to turn into a 0. So I get an entire row of zeros down at the bottom, as must always happen when I'm doing an eigenvector calculation. Okay, if I did not get a 0 row down here at the bottom, then I would know that I must have calculated my eigenvalues incorrectly. All right, now I'm in row echelon form. Okay, here's my one and only leading entry. 0 rows are tucked away at the bottom. Great. That's row echelon form. Okay, V1 is leading, V2 is free. Okay, so I want to get V1 in terms of V2. Well, what's this equation say? It says minus I times V1 minus V2 equals 0. Rearrange that so that you've got V1 in terms of V2, right? Leading in terms of free. So divide both sides by minus I. Okay, in other words, multiply both sides by I. Okay, and bring the V2 stuff over to the other side. And what you're going to get is V1 equals minus I times V2. Okay, so what's that tell me about my eigenvector? Well, my eigenvector is V1, V2. What is V1? It's minus I V2. So I throw that in the first slot. And then what is V2? Well, it's free, so it just is itself. Okay, and then as always, I can sort of factor out a V2 out of everything here. Okay, I can factor out my free variables. I'm just left with minus I and 1. Okay, so these are my eigenvectors. My eigenvectors are all multiples of minus I, 1. So a basis of my eigenspace is just, you take this single vector here. Okay, so that's the basis of my eigenspace. So sort of the big picture here is very similar to what it was when we were working with real numbers. It's just, well, if you get a complex eigenvalue, you're going to get a complex eigenvector as well. Now, this is the answer for one of the eigenvalues. You got to go through the other one as well. We've also got to go through this procedure for lambda equals minus I, except you don't really. The really nice thing is, remember, if you've got a real polynomial, eigenvalues or roots come in complex conjugate pairs. And that's what happened here, right? These are complex conjugates of each other, plus and minus I. The corresponding eigenvectors will also be complex conjugates of each other. So we know right away, hey, if this is a basis for my eigenspace of lambda equals I, then for lambda equals minus I, what's going to happen? Well, just take the complex conjugate of this eigenvector here, and I'm going to get my basis is I1 instead of minus I1. So I take the complex conjugate of every single entry in my eigenvectors. And that gives you a basis of the eigenspace of the complex conjugate eigenvalue. Alrighty, so that was a bit of a long one again, so thanks for watching, folks. I'll see you next time.